Hey y'all, we are looking at parallelism and scalar product in vectors today. Woohoo! The moment you've been waiting for. So if vectors are parallel, they need to be moving in the same direction. They can be different sizes though, right? You can be moving in a parallel line with somebody else and you move whatever 100 meters and your friend only moves 50 meters. As long as you're in the same direction, you're parallel, right? It doesn't matter the magnitude, right? So that's two vectors are parallel only if they're a scalar multiple of each other. So if this is 1a and this is 2a, they're still parallel, that's fine. And even if it's a third a, it's still parallel, fine. That's just because they, if you move up and over in the same direction and add two of them tip to tail, they're still moving in the same way, going from point A to point B in the same manner, and so they're still parallel. Great, fine. So we can do a couple of things with that. One thing that's important is these unit vectors you hear about and you have to work with a lot. And a unit vector is 1 unit long. So that's pretty simple if it's 1 unit in the x or 1 unit in the y, but it gets convoluted if it's 1 unit at a diagonal. Like this is not a 1 unit vector because this length between here and here is not, it's root 2, it's not 1. So it would be a partial distance like that, and this is a unit vector because it's 1 unit long. So we're trying to explore that. So let's look at this piece. This vector goes over 4 in the j direction. 1, 2, 3, 4. 1, 2, 3, 4. I guess I'm counting by 2's here for some reason. And up in the 3, up 3, 1, 2, 3, right? So there's 4 and 3. So the magnitude of this, the length of this is root 4 squared plus 3 squared. It's a 3, 4, 5 right triangle. It's 5, right? So the length of this should be 5. Hope that's comfortable so far. So if this thing is 5 units long, a 1 unit piece would be a fifth of the length, right? If the whole thing is 5 units long, we wanted something parallel but only 1 unit long, it would be a fifth of the size. So 1/5 is long, but it's still moving the same sort of way in the x and y, right? So we could take this thing and to find a 1 unit length, we'd break it into fifths. 1, 2, 3, 4. Oh, 1, 2, 3, 4, 5. Dang, I missed. You get the idea. So really, we can take this and take a fifth of it, right? So if we want u to be a unit vector in the same direction as v, you just take we want a fifth of v, right? We want a fifth of this. 1, 2, 3, 4. There we go. We want a fifth of it, so we want a fifth of this and this, right? So we could distribute that in. So that's what we're going to look at is unit vectors and then applications thereof. So they say that a unit vector is 1 over the modulus of a times that vector a. So if we have this and if it's length 4, right, a unit vector would be 1/4 of that size, right? So that's this piece, and I'll give you some examples. If this is a little blurry to you right now, it's okay. So if we want something parallel to A, right, something parallel to this, we know it's going to have this unit vector, right? It's going to have unit vector 1 over modulus of A times the A vector. But if we want it to be, I don't know, 2 units long instead of 4 units long, then you take all of that and you multiply by 2, right? You have a k value of 2. And if you don't care about the direction, just parallel, it can be plus or minus that. Let me give you an example of that, if that's a little fuzzy. So here's our vector. We want to find a unit vector in the direction of this A vector. Let's start with that. All right, well, this is 3 over 1, 2, 3, and 1 up, right? So here's our vector. So I want to figure out the length of this, right? So I want to figure out the length, which is also called the modulus, right, or the absolute value, whichever you want to think about it. Well, it goes 3 over and 1 up. So the absolute value of this would be root 3 squared plus 1 squared, so root 10. So the length of this green vector is root 10, which is not 1, right? So it's broken up into its root 10 length. And so if we want something that's only 1 unit long, it needs to be root 10th of that, right? If it was 3 units long, we'd want it to be 1/3 of that. Here it's root 10, so we want our new unit vector to be 1 root 10th of that piece. So that's what this piece says, right? We're finding the length of the original vector. Because the original vector is this long, root 10 is, I don't know, something is 3.16, right? Let's call it 3 for argument's sake, right? Or 3.16. Then a unit vector is going to be the same distance, right? Goes the same distance over, goes the same distance up. It has the same slope essentially, but it's 1 root 10th of that, right? It'd be 1 over 3.16 of that. And of what? Of the original. And the original is this vector, right? So here's our original vector. It is, this by itself is not 1 unit long. It's root 10 units long. So if we want something that's going the same direction but 1 unit long, then we want it to be 1 root 10th as big. And so that's what this piece is about, right? And you can distribute this in if you like and get this piece, right? If you're having trouble with fractions, come see me. Great, so that's all that jive. We also want to figure out in B the length of a vector that's parallel or in the same direction, just the positive, and also has a length of 4. Well, this is a unit vector. This is 1 unit, right? Long and moves in this direction. So if we want something with 4 units, you just take this thing and multiply by 4, right? So that's what this is. Ping. So that's what where this 4 shows up. We just took this unit vector that we had here in either form. It doesn't matter if you use this form or this form. And we just multiplied it by 4 to make it 4 times as long. Since this is a unit vector, its length is 1, and so multiplying by 4 gives us a length of 4 units. If we want all of the vectors with length 4, it's this, but you're multiplying by plus or minus that 4 because you don't care which way it goes. So one set is what we just found here. That's this, right? And the other set is if the 4 was negative, right? It just changes the sign. So those are the two. Those are the two that would be parallel. One's going this way, one's going that way, same length. All right. You try it. It's the same sort of thing. Here's our vector A. I want length 7, but in the opposite direction of the vector, right? So think about how long this thing is. It's moving this way. How long is A? And try to find a unit vector, and then try to change that unit vector so it's it's 7 times as long, but in the opposite direction. Pause me and try it. Go. All right, so to find the length of this, we just use Pythagorean theorem, right? We say the length of this vector is root a squared plus b squared plus c squared. So 2 squared plus negative 1 squared. Careful to put them in parentheses, plus 1 squared. Right? And when you do this, you get 4, 5, 6. You get root 6. Sorry about my terrible scribbling. That's the length of this vector, right? The absolute value, the length of it is root 6, which is not 1, right? If we want this to be a unit vector of 1, we have to make it 1 root 6 as long, and then it's a unit vector. Then it has a length of 1, right? So that's what this is about. This by itself has a length of root 6. So if we take 1 root 6th of that thing, now this is a unit vector. Means it has a length of 1. Ching, got it, fine. We don't want it to have a length of 1. We want it to have a length of 7. So if this is a unit, if this has length 1, just multiply it by 7, right? That's what this is about. So we've multiplied by 7 here, but because they asked us for the opposite direction, we choose -7. If it's the same direction, it's +7. If they say just make it parallel, plus or minus 7, because it can go in either direction. Cool. All right.